Good afternoon, everybody. Today's October 17th. I'm sending this video to kind of summarize today's activity. And for those of you who aren't in class, it'll be a really good hearing about what you'll miss. Kind of a bad day to miss because it was an interesting activity, a good day to miss because you've got this video to refer to. So I'm just going to point out that the document I'm going to open is down here in class materials. If you've forgotten, all sorts of class stuff is going to be down here, solutions to Dice Day. But before we even look at that, let me zoom in a little bit. What this activity required was go into a Google app that rolls these dice. It's a 6-sided die and a 4-sided die. When you roll, you get results like this. This would be a roll of an 8. You got a 4 on the 6-sided die and a 4 on the 4-sided die. And so that would be a way to roll an 8. You can also roll an 8 by rolling a 5 here and a 3 here, and so on and so on and so on. So we started this work just by saying, summarize what can happen when you do this. And so that we filled out this table right here. And let me jump down to the answer key to that down here. Which is basically, these are all the ways you could roll those dice. You know, if you rolled a 4 and a 3, that might be the 7 right here. Notice you could also roll a 7 by rolling a 3 on the 6-sided die and a 4 on the 4-sided die. You could also roll a 5 on the 6-sided die and a 2 on the 4-sided die. That would give you 7. Or rolling a 6 on the 6-sided die and a 1 on the 4-sided die would also give you a 7. So when you come up with this table, this is really the sample space, all the possible outcomes of the roll you could get if we thought of the roll as the total of the two dice. So there are 4 ways to roll a 7. So the theoretical probability of rolling a 7 would be 4 ways to roll a 7. There are 24 ways to roll a table altogether. So that would be a 4 out of 24 chance, which works out to be about a 16.67% chance. The word complement refers to sort of the rest of the possibilities. The number that complements 16.67% is 83.83% because those two numbers make 100% together. So your odds of not rolling a 7 would be 83.83%. So you might think I'll win the game if I roll a 7. Well, you have a 16.67% chance of that. I'll lose the game if I don't. Well, there's an 83.83% chance of that. So the thing to notice about this is these are all theoretical probabilities. We didn't have to roll a die in order for these to happen. And this is a very distinct thing. You had to have perfect dice that have an equal chance of rolling each side of the die. Life doesn't really work like that. Data really works like that. So on the second page of this, we actually went and conducted trials of rolling the die and got all this data. So this is, I typed this all into Excel. One table group rolled out of 50 times rolling those dice. They rolled a 2 5 times, a 3 once, a 4 5 times, a 5 11 times, a 6 5 times, a 7 8 times, an 8 6 times, 9 6 times, and a 10 3 times. So out of those 50 trials, they got these different numbers. But if we look at, say, just the 7 row right here, one group rolled 8, one group rolled 7, one group rolled 10, one group rolled 4, one group. There's all this variation. So that doesn't mean there's anything wrong with this website or this thing. It just means, it's random in that, it's not probably going to not roll exactly 16.67% of the times when you only roll 50 rolls. So for example, on that 7, the lowest number is 4 out of 50, which is about an 8% empirical probability. And the highest we saw was 11 out of 50, and that would be a 22% empirical probability. So those are quite a bit different than that 16.67% theoretical probability. So after class today, and nobody has seen this part, I combined all the data, and between all of those groups, there were a total of 500 rolls, 10 groups doing 50 rolls each. So of those total 500 rolls, there were 26 twos. So that would be an empirical probability of about 5.2% rolling twos, and a 31 threes. So that would work out to be about a 6.2% empirical probability, and on and on and on. But focusing just on the 7, for example, we already worked out the theoretical probability of rolling a 7 would be this 16.67% chance. But based on our class data, we got 78 sevens out of 500 rolls. So that's a 15.6% chance, empirical probability of rolling a 7. So notice that those numbers are different, but they're not that different. And this is a good example of the law of large numbers, which basically says if we keep rolling the die over and over and over again, the empirical probability should match the theoretical probability. If we did it 5,000, 50,000, 500,000, 5 million trials, we should see this number get basically to be exactly 16.67%. I had this other thing based on the theoretical probability of rolling a 6, 7, 8 would be based on the sample space. This table, theoretically, this is how it would all work out. And saying, all right, theoretically, there's 4 ways to roll a 6, 4 ways to roll a 7, three ways to roll an 8. So there's an 11 out of 24 chance, or a 45.83% chance of rolling a 6, 7, or an 8. And then using our class data, there were 86s, 78 sevens, and 75 8s. So there were 233 6, 7s, or 8s out of the 500 rolls. So that's about 46.6%, which is very close. That's less than 1% away from the theoretical probability. So it's another example of the law of large numbers. Even though your individual data didn't necessarily work out to be super, super close to the theoretical probability, when we combine our data, we see it getting a lot closer. Okay, that's it. That's all I'm going to really say in this video. I want to keep it short as possible, but follow up with questions if you have them, and I will answer. See you all next week or sooner if you want to meet over Zoom.